Thank you. It's been a fantastic week, and I'm really happy I got a chance to be here and listen to all those really inspiring talks that really synthesize all of the wonderful things Maxime has been teaching us throughout the years. So I gotta say an anecdote too, right? I mean, everybody is telling one of those. So I met Maxime for the first time 20 years ago, and I tried to talk to him about deformation quantizations of K3 surfaces, and he wasn't interested in talking about that because he knew the answer. And he said, "Okay, I'll explain it to you in a moment, but let me tell you this great thing I just saw." I was riding the bus in Cambridge, that was in Massachusetts, and I saw a billboard with a quote from Albert Einstein saying, "Imagination is more important than knowledge." So this is actually much greater than deformation quantizations of K3s. And I didn't believe him, but you know, now I'm older and to a large extent because of Maxime wiser, so I see how great that lesson was. But anyway, it took me. Huh? I don't remember. That's okay.
I wasn't there, but then you gave a talk at Harvard, and this was the first thing you said.
I wrote this here, I can see.
Yeah, this was
no, he was really excited about that billboard, and yeah, I really wanted to talk about that. And anyway, so I want to talk about this story about foliations and potentials in shifted in derived geometry, and it's based on a couple of joint works with a subset of all of those people that Bertrand already mentioned, with the addition of Ludmil. Yeah, right. It's a typo. So what this story is, it's about understanding foliations in derived geometry and the leaf spaces of foliations in derived geometry. And the reason you're interested in that is because, in fact, isotropic and Lagrangian foliations in shifted symplectic geometry turn out to be closely related to the existence of potentials. And so there is this old puzzle which we face as mathematicians coming from mathematical physics, which is that moduli spaces of geometric objects or a vacuum or for whatever the physicists are interested in physics are always given in some global way as the critical loci of potentials. Whereas for us, there are some intrinsic objects that have nothing to do with any ambient spaces, any actions or anything like that. And in fact, very often, the spaces we describe may not even be describable as critical loci of potentials. And so in that sense, they're not physical. And so there is this conceptual problem of trying to understand which moduli problems arise as critical loci of potentials. And this story with the foliations actually comes as a mechanism for providing an answer to that problem, especially isotropic foliations. And so, yeah, so I'll talk about these leaf spaces of foliations and their relationships to the Derived theorems in derived geometry. And the most interesting part of the talk will be the examples and two general constructions for producing these foliations and potentials, which are, I think, quite intriguing. So I got to apologize for about 20 minutes. It's going to be kind of dry because I need to set up the language and explain the concepts that we're going to be working with. But once we have that under our belt, we'll start actually seeing some interesting geometry. So bear with me for a while. Don't fall asleep. Okay. So here's the setup. I'm going to talk about foliations first in the affine setting. So suppose that we have a non-positively graded, commutative differential graded algebra over the complex numbers, the same way it appeared in Bertrand's talk. And we're looking at the derived scheme, which is the spectrum of that. And so the most economic way to define a foliation, which is not the way you really think about them and work with them, but for pedagogical reason is best to think about it this way. It's a mixed graded commutative differential graded algebra such that its weight 0 piece is isomorphic to our algebra functions on the derived scheme. And there are two conditions. The weight 1 piece is a perfect module. So it's like a vector bundle on our derived scheme. And ignoring the mixed structure, ignoring the second differential, this algebra is freely generated by its weight 1 piece. And since it's going to be relevant, let me just recall what a mixed graded commutative differential graded algebra is. So it's a bicomplex. It's a bi-graded vector space, which is equipped with a graded product, which is associative, which is graded commutative with respect to either of the two gradings. So one of the gradings is written as a superscript, that's the homological grading, and one is written in parentheses, it's called the weight grading. And it's equipped also with two derivations for the product. One is of homological degree 1 and weight degree 0. And the other is homological degree -1 and weight degree 1. And those anti-commute, so they give you a bicomplex. So it's a bicomplex which has a cohomological differential and a homological differential, but also has an algebra structure. So that's what a mixed graded commutative differential graded algebra is. And
can you remove your telephone?
oh. That's the problem. Okay, thank you. This is really what a foliation is, but let me try to explain that and reformulate it in a way that's more familiar and makes it easier to work with. Since as an algebra, as a differential graded algebra with a homological differential, but ignoring the mixed structure, the other differential, it's freely generated by its weight 1 piece. I can actually describe it in terms of that perfect complex, which is the weight 1 piece. But before I do that, let me just give you the two standard examples, which are really the model examples of what's going on. One is the trivial foliation, which is given by the weight 0 piece is our algebra, that was part of the definition, and there is no weight 1 piece. The weight 1 piece is 0. And then there is the tautological foliation, which is given by the de Rham complex. So you have the cotangent complex, which is the complex of forms on our derived scheme. And it has a homological differential because it's a complex, and it also has a mixed structure, which is the de Rham differential. And so the only non-familiar thing here may be the fact that I've chosen a weird grading. I've shifted the form degrees so that all my forms sit in negative degrees. And that's so that we have compatibility with cyclic homologies and functions on the loop space. But it's not really essential. I mean, it's just a convention. Okay, so these are the two standard examples of foliations, and they really model what's going on. So you can say what a foliation is in this language in terms of the de Rham complex. So you can think about it as a triple. L is a perfect module over our derived scheme. We have an anchor map from the cotangent complex to that perfect module. And we have a mixed structure on the free algebra generated by that perfect module, shifted by 1, so that the algebra map induced by the anchor map is a map compatible with the mixed structure. So intertwines the de Rham differential on, do I do this right? The de Rham differential on the de Rham algebra with the one on the foliation.
Sorry, Tony, why is it called foliation? So foliation is something on manifold.
I'm explaining. It's coming. Yeah, so there is a dual notion of that, which is, so if you dualize this perfect complex to the dual perfect complex, then the mixed structure dualizes to a differential graded Lie algebra structure. You still have the anchor map, and again, the condition is that it gives a morphism of shifted Poisson commutative differential graded algebras. So this is more familiar. This is similar to the classical notion of a foliation when you talk about an integrable distribution in the tangent sheaf. The only difference with the classical differential geometric notion is that there is no injectivity condition because we're in the derived world. So any morphism works. So you can, in the previous one, on the previous slide, we had it as quotients of the de Rham algebra. Here we have it as Poisson subalgebras in the algebra of vector fields, and or of polyvector fields. You know, they're not really quotients or subs. They're just things to which the de Rham algebra maps, or things that map to the vector fields. That's the only difference that that's specific to the derived setting. So these are all equivalent data. The data of the mixed CDGA, or the one coming with coming from the cotangent complex, it's actually better than the one coming from the tangent complex when you start doing descent. So the ones that's written in terms of forms, it's much better adapted to writing gluing conditions.
There was also foliations of examples of simple examples of Lie algebroid.
Yeah, so the previous slide, the thing that we have is really a Lie algebroid in the derived setting.
But Lie algebroids can be suits again some DJ manifolds, which is kind of contained.
Yeah, exactly. Yeah.
The conventional foliation, they give a special example, but is it kind of unique?
Say it again?
Can the commutative kind of...
No, in Lie algebroids is particular case.
Yeah, a Lie algebroid, even in ordinary differential geometry, is a particular case of a foliation in this sense, but may not be a foliation in the ordinary sense, depending on the behavior of the anchor map. Okay, so this is what happens on affine guys, and then you can map foliations to each other by saying that you have maps between these vector bundles that generate the foliations, and they intertwine the anchor maps and the mixed structures. So this is what happens on a given affine guy. And now the interesting thing is, because you want to glue these, you have to say how you base change them. So if you have a morphism between affine derived schemes, which comes from a morphism of CDGAs, you can ask on how to base change, and you base change the same way you base change Lie algebroids. So you pull back so there is this notion of a base change of foliation, which is not the pullback of the vector bundle that generates the foliation, but it's a pull-push construction. So you pull it back, so you base change by tensoring with algebra A prime, and then you take the push out under the codifferential, which is the map on the cotangent complexes, and that's the base change of the foliation bundle. And once you define it that way, then the mixed structure descends along the right morphism, and that gives you a notion of a foliation. The anchor map is the one just tautologically defined by this diagram. So that gives you a notion of base change of foliations. And again, let's look at some examples. If you take the trivial foliation, then when you base change it by a morphism, you get the foliation which is tangent along the fibers of the morphism. And I'll talk about it. I haven't defined it. I'll define it a couple of slides later, but it should be obvious, say, in the ordinary differential geometric setting what that one is. Just vector fields tangent along the fibers. If you base change the tautological foliation, you always get the tautological foliation. Right? So the RAM complexes, they are functorial. And here is a amusing example. If you take a point, a foliation on the point in this derived setting is just a differential graded Lie algebra. And the base change along a morphism is a split foliation. It's the foliation that's this differential graded Lie algebra extended by linearity on your space time plus the vector fields with the standard Lie bracket. So, okay, so hopefully this gives you some sense of what these guys are. And the good thing about this base change is that it allows you to do descent. And you can define now foliations for derived spaces and derived stacks. So you can look at the assignment that goes from derived affine schemes to the space, the mapping, the classifying space, the groupoid of foliations on the affine scheme. And this is a stack in the étale topology with this base change notion. And then you can define a global foliation as an element in the mapping stack. If you have any stack, derived stack, which on the in the étale topology on the stack of affine schemes, you can take the map from that to foliations. And that's a pattern in this derived stacky geometry. The stackiness is always a problem because a lot of notions that we want to work with, like forms and vector fields and differential operators, they have bad descent properties with respect to smooth morphisms. And you have to stackify every time you try to globalize them. They make perfect sense on affine locals, but once you start to globalize, you need to do something like cohomological descent on hypercovers. And that's what this thing actually achieves. So there is I don't want to spend time, there is a way to actually write that in terms of local data on affine derived schemes that probe your stack. But I don't want to go into that, so I'm going to skip that part.
Sorry, but excuse me, is it a groupoid or a high groupoid? I mean,
it's groupoid means an infinity groupoid for me. There are no truncated things. Yeah, there are no truncated things in this talk. Yeah, everything is infinity. Yeah, so the tangential foliations that I promised. Suppose you have a morphism of derived stacks, a locally finite presentation. The tangential foliation is given, so I didn't give you the description in terms of local data, but it is the vertical tangent complex, the cotangent complex along the fibers of the morphism. If you want to write it in terms of an anchor map and mixed structure, you have to take the big cotangent complex on the big étale side because the RAM differential doesn't exist on the quasi-coherent cotangent complex globally. And the anchor map is just the restriction from global forms to vertical forms. And yeah, so this is the relative cotangent complex. You have the restriction map from global forms to vertical forms that, of course, if you take the quasi-coherator acting on the big cotangent complex, you get the quasi-coherent cotangent complex, and this gives you the restriction map. And the only thing that doesn't exist on the quasi-coherent version is the RAM differential, which you have to keep there. So that's the tangential foliation. And this is an important remark, even though it's not gonna, well, it's gonna appear in one of the examples, but it's not gonna appear essentially in this talk, but it's really important, so let me make it. You can define the tangential foliations for morphisms which are not morphisms of algebraic derived stacks and are not locally finite presentations. And there are many important examples where you really need to do that. So they make sense when the target is a formal derived stack. And again, this is slightly delicate, so I'm going to skip the technical definition. Locally finite presentation. The formal derived stacks do not even need to be locally finite presentation. They can be almost locally finite presentation, which means that they have cotangent complexes with coherent cohomologies, but maybe unbounded Tor amplitude. And they can also be informal derived stacks, almost of finite presentation locally. And these actually have been studied extensively by Nick Rosenblum, and there are many important examples coming from representation theory, which are exactly of that type. Yeah, so I said the quasi-coherator will not be perfect, but in this case will be with coherent cohomology and unbounded Tor amplitude. And let me just give you some examples of these guys to convince you that they're important geometrically. They arise really naturally. One example is a formal stack that Bertrand discussed last in his lecture is the RAM stack, which will reappear very soon and play a very prominent role in our discussion. So it's a formal derived stack of locally finite presentation, but it's not algebraic. The derived Hilbert and Quote schemes of Chiu-Kang, Fontanin, and Kapranov, they are almost locally finite presentation. And run spaces are informal and almost locally finite presentation. So all of those are important, and you would like to work with them, and they do appear when you start dealing with geometric settings all over the place. Okay, let me just, since I'm talking about tangential foliations, let me just mention two examples. The trivial and the tautological foliations are tangential. The trivial foliation is just the tangential foliation for the identity map. And the structure morphism to a point gives you the tautological foliation. So those are particular examples of tangential foliations. And in fact, with the exception of one construction in this talk, all the foliations we'll be dealing with will be tangential. Okay. Now, the one thing that we really want to extract from this formalism is Leaf spaces. So we want to be able to take a derived guy and quotient it by a foliation. And as in usual geometry, the output of that process is not going to be a space, but it's going to be, or a stack, it's going to be a formal stack. And so you have to actually, depending on the generality of formal geometry you want to allow yourself, you have to work a little bit for that. So here is a definition which is actually a theorem. So this is what Bertrand mentioned. So these quotients are defined by a universal property, and they exist. So if you have a derived stack locally finite presentation and a foliation on the derived stack in the strict sense, so given by a perfect guy, then there exists a formal derived stack, which is the Leaf space of that foliation, and a quotient map. And it's uniquely characterized by a universal property. The universal property is that if you map X to any other formal derived stack, so that the tangential foliation to the map, to the test stack, maps to the given foliation, then that map on foliations induces a unique morphism on the quotient, from the quotient to the test map. And this is unique. So that's the universal property, and you can construct these Leaf spaces, which are formal stacks, and we'll be using them very soon. So again, the reason, maybe let me just say a little bit about quotients. They behave exactly as you expect them to behave. First of all, these quotients are really sensitive to nilpotents or to derived structures. I mean, if you reduce everything, so if you truncate to something which is non-derived and pass to reductions, the quotient by foliation gives you an isomorphism as a higher underived stack. So the quotient by the trivial foliation doesn't do anything, just gives you x. The quotient by the tautological foliation gives you exactly the de Rham stack, which Bertrand defined it. You attach to a commutative differential graded algebra the points of x on the reduction of that, which means first you kill all the derived pieces, and then you reduce by nilpotence. And this is Carlos's definition of the de Rham stack. And when you work out this universal property, this is exactly what you get for the quotient by the tautological foliation. If you take the cotangent complex for the leaf space, it is exactly what you expect it to be. It's the cone of the map from the cotangent complexes from X to the foliation bundle. You can, in fact, ignore the nilpotence in X. You need to keep the derived structure, but you can ignore the nilpotence. So you can kill the derived structure, kill the nilpotence, take the reduced underived space sitting inside as a closed subscheme in your derived stack. You can base change the foliation. Now, this is not going to be foliation in the strong sense. It's not going to be perfect. But it will be int locally almost a finite presentation. And then the map on quotients is an isomorphism. So we can't prove it in this generality. We can only prove it for the strong foliations, for the perfect ones. So this thing exists in this particular case, but in general, we don't know how to prove it for general foliations, which are almost locally finite presentations. OK. Now, if you have a reduced algebra of finite type, nothing derived, not non-DG, and you have a foliation, derived foliation on it, then the algebra of functions on that leaf space is exactly what you expected. It is the completed, so the total complex, the negative cyclic complex of the completed symmetric algebra of L shifted by -1. So it's just, you have this mixed complex and you take its total complex. So again, if you understand formal spectra properly, which is what Bertrand was discussing in his lecture, in the affine case, the quotient by the foliation is just the formal spectrum of this total complex of the de Rham algebra of the foliation. So here is probably the most useful example. If you have a morphism of derived stacks locally finite presentation, and you look at the tangential foliation, then the quotient is the relative formal completion of X along the fibers of F. So what you have to do is the derived stack, whose value on a commutative differential graded algebra is the fiber product of the points of it's the fiber product of the points of the target over A with the reduced points of X over the reduced points of the target. So, if the target was a point, you'll get exactly the de Rham stack. So this is like the family of de Rham stacks along the fibers. And there is a reason why we call it a formal completion, because if the morphism is a smooth morphism of schemes, then you really get the relative de Rham stack along the fibers. But if it's a closed immersion, you get the formal neighborhood. You get the functions on the formal neighborhood of X inside Y. So you get the formal completion of Y along X. So there is a slight caveat in this isomorphism, but it's technical. I'm not going to discuss it right now. But they are isomorphic if you interpret the what isomorphic means correctly. They're extra structures which are not quite matched, but as algebras, they're isomorphic. OK, so we have these very nice properties of quotients, and we have this relative completion, which is a quotient by the tangential foliation. And now I want to bring the symplectic geometry into this game and see what can we say if we have not just foliations, but have foliations which are Lagrangian or isotropic. So if you have, say, a fine derived scheme and an n-shifted two-form, which doesn't have to be symplectic, just closed n-shifted two-form. So in algebraic language, it's just a morphism from this mixed graded commutative differential graded algebra generated by a piece in one homological degree 2 minus n and one weight degree 2 to the de Rham algebra. And so that's what a n-shifted closed two form is. An isotropic structure on such foliation is just a homotopy between the induced morphism to the foliation from the symplectic form with the anchor map and the zero map. So that choice of a homotopy is a structure. You need to keep track of it, but that's what it means for the foliation to be isotropic. And you can also define a Lagrangian foliation. Yeah, I mean, I actually wrote down here explicitly how you write isotropic structures in this derived sense. You can write closed two forms as infinite sequence of forms, terms sitting in terms of the cotangent complex with the corresponding degree, which are annihilated, which are cocycles with respect to the total differential in the double complex. And then H is just a cochain that bounds that form in the double complex corresponding to the foliation. So it's something in the affine case. It's something very explicit. I mean, it has a large amount of homological data on it, but it's something completely explicit. I mean, it becomes complicated when you start gluing things. And then you can play that game with gluing again. You can define a morphism of isotropic foliations. You can define a base change of isotropic foliations. This is where you need the form not to be non-degenerate, because when you start pulling back, non-degenerate forms can become degenerate, but we don't care. I mean, the notion of being isotropic doesn't care about non-degeneracy. So you can define base change of isotropic foliations, and again, the same trick works. The assignment that sends a shifted symplectic, or affine scheme with a shifted closed two form to the groupoid of isotropic foliations is a stack in that topology, and you can define a global isotropic foliation as an element in the mapping stack. Then you can put a non-degeneracy condition on the isotropic foliation once you have one for a non-degenerate two form. Then the non-degeneracy condition is a purely algebraic condition. It's just the condition that says that the foliation is isomorphic as a perfect complex to the conormal bundle of the map. So you just write down the composition with the symplectic form to the quotient by the foliation, and you want this to be a quasi-isomorphism. So it's exactly, I mean, it's a complicated formula, but it's just the most naive thing you can do. It's the standard notion of being Lagrangian. So the reason we care about these guys is, as I said, because, so this is Lagrangian when it's a quasi-isomorphism. And the reason we care about them is because we want to talk about potentials, and this is related to the Darboux theorem. So in classical symplectic geometry, the local structure of a symplectic manifold is given by the Darboux theorem, which says that, say, locally in the C-infinity setting, or formally in the algebraic setting, the symplectic manifold is isomorphic to the standard symplectic structure on a cotangent bundle. And you would like to have something like that in this derived symplectic geometry. The problem is that you have more cotangent bundles, more than one cotangent bundle. So you have more potential local models than just a cotangent bundle. So the most naive thing you can do is what Bertrand described in his talk is the shifted cotangent bundle. So you just take the tangent bundle shifted by minus n, take the symmetric algebra, and take the spectrum of that. That carries a natural, exact shifted symplectic form. So that's a perfectly nice linear shifted symplectic manifold, differential graded manifold or a stack. The problem is that not every shifted symplectic derived stack is isomorphic locally to this. So there are deformations of these guys which are not locally isomorphic to them. So the derived critical locus of a function is equipped with an n-shifted symplectic form, and in general is not locally isomorphic to a shifted cotangent bundle. So if you have a function mapping you to the n plus first shift of the line, so you can think about this as a degree n plus 1 cohomology class with coefficients in the structure shift of n. It has a well-defined critical locus which is equipped with a symplectic structure which is shifted by n. So there is a drop-in shift by 1 because this is a Lagrangian intersection picture. So if you have a shifted function, n plus 1 shifted function, its derived critical locus is equipped with an n-shifted symplectic form. If that function is constant, then you get a shifted cotangent bundle, or locally constant, then you get a shifted cotangent bundle. But if it's not constant, then the derived critical locus is not necessarily isomorphic to a shifted cotangent bundle, and that's very easy to see in examples. So you have a choice here whether you think about these guys as your local models or these guys, and since I said these are more general, they don't specialize to this even locally, it's better to use those as your local models. And so if you have a hope for a Derbout theorem, you want to say that a shifted symplectic manifold is locally isomorphic to the derived critical locus of a shifted function. And so that's what we want to do. And this leads to this remarkable Derbout theorem that Dominic Joyce and his group proved. If you have a derived Deligne-Mumford stack with an n-shifted symplectic structure, where the shift is non-positive, then et al. Locally, it's isomorphic to the derived critical locus of a shifted function. So this is Dominic Joyce and his postdocs, graduate students. In fact, on schemes, it's risky locally. So it's a very strong statement. And now the problem we were trying to solve, where these foliations were needed, was to try to understand what's the ambiguity in this, the choice of these local structures, and when can we hope for them to be global? So this tells you that locally you always have a potential, but maybe sometimes you have globally a potential. So when can you hope for the potentials to exist globally? And so this is what the foliations help you answer. So the point is that potentials always exist if we have an isotropic foliation. So here is the theorem. Suppose that you have a derived stack locally finite presentation and an n-shifted symplectic form on it. And assume it's exact. Of course, if you want to have a potential, it better be exact. The ones that are shifted symplectic forms on derived critical loci are always exact. Suppose that it's equipped with an isotropic foliation, so a foliation with an isotropic structure H. Then the claim is that on the leaf space of that foliation, there is a shifted function, n plus 1 shifted function, and the map from X to the leaf space factors through the derived critical locus of that function. And in fact, not only factors, but it's symplectic. It pulls back the shifted symplectic form on the derived critical locus to the original shifted symplectic form. And that's completely global. If the foliation exists globally, then on the leaf space you get this function, and you can identify the whole space as a derived critical locus. If in addition the foliation is Lagrangian, then that map to the derived critical locus is also a tau.
Yeah, it's kind of, it's something called super manifold. People get odd vector field preserved Lagrangian foliation. Yes,
Yeah.
have vector fields on the base and
No, it's a very natural. Yeah, it's a very natural statement, and it's actually not very hard to prove once the technology is set up. I mean, you know, where is the function coming from? It's coming from the fact that the form omega is 0 on the leaves of the foliation for 2 reasons. It's 0 because it's exact, and it's 0 because the foliation is isotropic. So you can find a homotopy between these 2 zeros, and that's the function. I mean, it's just as simple as that. And it really connects with the result of Joyce and company, where there was no exactness condition, but there was the condition that we were local with non-positive shift. And the point is that if you work out through the Hodge theory, it turns out that if you have a closed p-form which is n-shifted with a negative shift, it's always exact. So that's something very peculiar for forms with negative shifts. And this is not a tautology. I mean, it's a statement with content because the corresponding de Rham cohomology is not 0. So this is really a property of this mixed complex of forms. Okay, so let me show you examples, and I want to really show you 2 constructions of these global potentials that come from these foliations, which are cool. So, of course, the basic example is a derived critical locus. If you have a smooth scheme and a regular function, so this is just an underived ordinary scheme, then you can take the derived scheme X to be the derived critical locus of W. It has a -1 shifted symplectic structure. Now, this better be coming from a potential. We know it's coming from a potential, but in fact, this potential is coming from a foliation. What's the foliation? You have the map from this derived scheme to Z. And you can look at the tangential foliation for this map, the inclusion map from the derived scheme to Z. And it has a Lagrangian structure, which you can write explicitly in terms of the function W. And the quotient is exactly the formal completion of Z along the underived critical locus. And the potential is just the restriction of the function to that formal completion. And the map is just the map from the derived critical locus to the formal completion. And the pullback of the symplectic forms is the fact that the pullback of the function is the pullback of the function. So this is a tautology, but it should be there as a check that what we are doing is correct. And you can do this with shifts. So this was for an unshifted function. You can do it for a shifted function. And again, you get the same foliation gives you a shifted function. And again, you get the potential is a pullback from the formal completion. Another example, if you take a cotangent bundle, so you take a smooth manifold, it's cotangent bundle with the standard symplectic structure. Then you have a projection from the cotangent bundle to M with Lagrangian fibers. The tangential foliation is Lagrangian. The quotient by the tangential foliation is, of course, as an underived space or as the space underlying a stack is just the total space of the cotangent bundle, but the fibers are completed in the de Rham sense. So it's the de Rham stacks of the fibers, the family of de Rham stacks of the fibers. The function is just 0, but viewed as a one-shifted function. And the derived critical locus is the shifting of the one-shifted cotangent bundle, which is just the cotangent bundle. So again, in this case, you get exactly what you expect. More interestingly, you can do twisted cotangent bundles. So suppose that you have a smooth manifold and you have a symplectic twisted cotangent bundle. So those are classified by elements in the hypercohomology of the stupidly truncated de Rham complex in degree 1. So They are affine bundles over the cotangent bundle equipped with a symplectic form corresponding to that class. The tangential foliation mapping to the base is still Lagrangian. The problem is that the symplectic form is not necessarily exact anymore. Twisted cotangent bundles are not always exact, depending on the twisting. If the symplectic form happens to be exact, then you should be able to find a twisted function, one-shifted function on the RAM completion of the fibers. And it's actually not hard to identify it. If you see where this function should live, it should live in the degree 1 cohomology of M with coefficients in the structure sheaf. And it is just the function, the class there, that bounds the class eta. So it turns out that eta will give you an exact twisted cotangent bundle exactly when it's in the image of the RAM differential with respect to the Hodge filtration. And whatever bounds it is exactly the function. So, and then you get identification of this with the derived critical locus. And let me just point out that this is, of course, interesting on M's which are not compact, because this function f is not going to be unique. It's going to be unique only up to a function which is locally constant, or only up to something that's coming from H1 with coefficients in C. And of course, if we had something locally constant, then there is no shift because d of f is 0. So what you really get is a shifted cotangent bundle again, or the original unshifted twisted cotangent bundle. So you cannot have M to be something for which the Hodge theorem holds if you want to get interesting examples. But for affine M's, you get interesting examples. Okay, one purely derived example, and then I'll give you the. How am I doing with time? 10 minutes?
Yes, 15 minutes.
Okay, great. So a purely derived example, which is neat. So suppose that you have a symplectic manifold, which is a point with the zero symplectic structure, but you view it as a one-shifted symplectic structure. The zero symplectic structure you can put in any shift. So on a point, you can talk about shifted symplectic structures of any shift. So we can actually describe Lagrangian foliations. If you have a finite dimensional vector space, and you look at the map from the point to the classifying stack of that space, so the stack classifying affine space is modeled on that vector space. The tangential foliation is given just by the dual space with the zero anchor map and the zero mixed structure. An isotropic structure is a self-homotopy in this negative cyclic complex that has a zero differential. So it's actually an element in the second wedge power of the dual space. And it's Lagrangian if and only if this element is non-degenerate. So if and only if V with this two form is a symplectic vector space. So a Lagrangian foliation for this. A situation in which this map from the point to the classifying spec of a vector space is a Lagrangian foliation, if the tangential foliation is Lagrangian, it's just the choice of a symplectic structure on the vector space. Now, the quotient by this Lagrangian foliation is just the classifying stack of the formal group, which is the completion of V at 0. And by the theorem, there should be a two-shifted function from that formal group, from that classifying stack to A1, two-shifted function, so that the point with the zero-shifted symplectic structure is the derived critical locus. And so in order to find that function, you need to compute the second cohomology of BV hat with coefficients in O. And you can actually do that because we have the Brin calculation. Which in characteristic 0 was redone by Carlos. And it says that if you have a finite dimensional vector space and you look at the Eilenberg-MacLane stack KVN, then the ith cohomology of KVN with coefficients in O is either a exterior algebra or a symmetric algebra, depending on the parity of N, or it's 0 if the degree over the homotopical degree is not an integer. So in particular, in this case, when we're doing something two-shifted, the answer is exactly wedged to a V duo, and the function is just H. So, it's a complete circle. Okay, so I have another example about integrable systems, but I'm going to skip that, even though it's interesting. I want to show you two constructions of isotropic foliations, one of an isotropic foliation and one of a Lagrangian foliation, which are interesting and give you new realizations of moduli spaces of critical loci of potentials. So suppose that we have a oriented C-infinity manifold of odd dimension, compact. Choose a Morse-Mel function, so it's a self-indexed Morse function, where the critical values are the indices. And choose a regular value between the two middle critical values. So now, if you take the half of the manifold that corresponds to everything smaller than that regular value, you get a submanifold with boundary, which when you include it in M, you get a homotopy equivalence on the k-dimensional skeleton. In fact, any such guy will do, but I mean, this is a way to construct it. Now, if you have a complex reductive group and you look at the derived stack of local systems on M, so these are maps from M to BG as a derived moduli, then this guy carries a 2 minus d-shifted symplectic structure, as Bertrand explained by this AKS-Zik formalism. And if K is greater than or equal to 1, this 2 minus d-shifted symplectic structure is negatively shifted. So by this theorem that I mentioned about the Hodge weights, it's exact. So you have this derived stack of local systems on an odd dimensional compact oriented manifold. As soon as the dimension is bigger than 1, it is an exact shifted symplectic manifold, or shifted symplectic stack. And the claim is that the tangential foliation for the restriction map from local systems on M to local systems on this half, this Hilbert half of it given by the Morse function, has a natural isotropic structure, depends only on the orientation data and the shifted symplectic form. And so you can find a shifted function, 2 minus 2k shifted function, on the quotient by that foliation, which is the relative de Rham stack. And the moduli of local systems with its shifted symplectic form is the critical locus of that. So for 3 manifolds, this just gives you an incarnation of the Chern-Simons functional if you choose a Hilbert splitting. And this gives you a generalization of the Chern-Simons functional to higher dimensions. But unfortunately, the off-shell space has no natural interpretation of a space of connections. It's really very derived. So that's one construction. The other has to do with non-abelian Hodge theory. So it's very similar. Maybe I didn't say that. So you can prove that this structure is isotropic. Unfortunately, we cannot prove it's Lagrangian. I believe it's Lagrangian. So that the map is really a tau. And in fact, like when M is simply connected, we can prove it's Lagrangian. In any case, I mean, under some topological conditions, we can prove it's Lagrangian, but we cannot prove it in general. I think it's just stupidity. But it's certainly isotropic, so it is really a pullback of a derived critical locus, symplectic form on a derived critical locus.
Is there a shift of vanishing cycles for this?
You mean for shifted functions? Yeah, you can define shifts of vanishing cycles for shifted functions, but because these are formal stacks, you really have to be very careful with your the boundaries properties of your complexes. So we can formally define it. I'm not sure that it actually exists because the cons may not be well defined if it's unbounded complexes. We haven't tried really. I mean, it just you can try to mimic the standard definition, but that maybe if you don't have bounded above complexes, maybe you're not going to be able to do it. So. Okay, but let me do this example. So suppose that we have a smooth projective variety of dimension D, and you look at the moduli stack of rank n local systems, again as a derived stack. So this is now equipped with 2 minus 2D shifted symplectic structure. And as Bertrand pointed out, this stack X, it has a tangent complex, and the tangent complex has a natural Hodge filtration from non-abelian Hodge theory, coming from the moduli space of lambda connections. So if you look at the relative moduli of lambda connections, in fact, the shifted symplectic structure exists relatively in the twistor space. And this, the C star action on the moduli of lambda connection gives you the Hodge filtration on Tx. And the map given by the contraction with the symplectic form actually is a filtered quasi-isomorphism for the Hodge filtrations. And as a consequence, if you look at the middle degree, the middle step of the Hodge filtration, the degree step of the Hodge filtration when D is odd dimensional again, this middle step of the Hodge filtration has a canonical Lagrangian foliation structure for the shifted symplectic form. It also works on the Higgs moduli, but here it's more interesting because on the Higgs moduli, everything is split. So you can take this foliation quotient by it and get a potential. So you can write the moduli of local systems on an odd dimensional projective manifold as a critical locus of a potential. And in fact, this foliation given by the middle step of the Hodge filtration is again a tangential foliation. So you have the local systems, the derived stack of local systems, rank n, and you can look at the derived stack of modules. So this is like dg modules over the full de Rham complex of M, which as all modules are of rank n. But you can look at dg modules over the truncated de Rham complex in the middle step of the Hodge filtration. And you have a restriction map from those. And the middle step of the Hodge filtration is just the tangential foliation for that. So if K0, if we are doing curves, then this is just the ordinary map from the moduli of local systems to the stack of bundles. But the moment we go in dimension bigger than 1, this map actually on truncations, so this is just the truncation, right? But this map on truncations is an isomorphism. So you don't get a new space, but you get a new derived structure. And the full untruncated stack is recovered as a critical locus of a shifted function on the relative de Rham stack. And you can actually identify that function explicitly there in terms of the symplectic structure. And I think I'll stop here.
Any questions to the speaker? Okay, so in this case, thank you very much.